Now, in question 7, part A, we're given that y equals the square root of tan x, and this table of values, and we have to fill in these three values here. Now, all you're going to have to do is just type these into your calculator, but I can see one common mistake, and that is make sure your calculator is in radians mode. And if it is, giving you answers to 5 decimal places shouldn't be much problem. So here are the answers. Okay, I'll just put them up for you. Okay, there they go, are in red, and hopefully you've got those right. Remember though, they're to 5 decimal places. Well, that was part A, and moving on to part B, what they wanted us to do is to find out the approximate area under the graph between the limits x is 0 and pi upon 4. And to do this, to find the area, if we were working out it exactly, we would have to work out the integral of y with respect to x, with x going, as I said, from 0 to pi upon 4. Alright? Now, that's the exact answer, or method I should say, but if we're going to use an approximate method, then they've asked us to use the trapezium rule. And I'm assuming that you would know the trapezium rule. If not, I've done a video tutorial. Just go to my website, look under tutorials. For the trapezium rule, you'll find it. So I'm working on the assumption that you know how to do this. So, according to the trapezium rule, it is half the width of each interval, and the width of each interval, you can see from the table, is going up in pi over 16. So it'll be half of pi over 16. Then it is always the first y value, which in this case is 0. I'll put it in even though it could be left out, plus then it's twice the sum of all the middle values, the middle y values, that's the ones in red here, so it's twice the sum of these, so we'll just write that in, 0.44600, that one, next one, plus 0.64359, and then plus the last one, 0.81742. Okay, so it's twice the sum of all the middle values, and then it's plus the last y value, which in this example is 1. Close the square brackets off, and then just use a calculator to work this out. And if you use a calculator, you find that you should get 0.472615, okay, and so on. It doesn't have to be in radians mode anymore, your calculator, because you're not doing the sine, tan or cos of any function. In this particular question though, we were asked to give the answer to 4 decimal places, so it will be 0.4726. And don't forget to put 4dp on the end. Alright, so that brings us to the end of part B. And finally, in part C, we've got to work out the volume of revolution when the area is spun about the x-axis. Now, the volume of revolution, we'll call it V, okay, or actually we could just say volume, that's better. Volume equals pi times the integral of y squared with respect to x, and it will go between the limits of x is 0 to pi upon 4. So put that in, 0 to pi upon 4. Okay, now we've got to work out the exact value, so we need to work out this integral, and we know that y is the square root of tan x, so when we square it, that will be just simply tan x. So I'll move this up, okay, give us more room, and carry on. So we have pi times the integral from 0 to pi over 4 of y squared, which we said was tan x, and that's integrated with respect to x. Now, the integral of tan x, you should know this, but if not, I'll show you how it's done. It goes from 0 to pi upon 4. Tan x is sine x over cos x, okay, with respect to x. Now, we have a fraction here, and like all fractions, the first thing I do is check to see whether it is of the type, and I'll just jot it down here for you, f dash x over f of x. That is the differential of the bottom the top? Well, the differential of the bottom cos x is negative sine x, and essentially it is, okay, because if you get one of these integrals, it reduces down to the natural log of the mod of f of x plus c. So I can see that this particular integral reduces down to the natural log of the mod of cos x, but if I differentiate natural log of cos x, I would end up with minus sine x over cos x. So I need to correct for that, and so I put a minus in there. Okay? And that is going from 0 to pi upon 4. If you look this up in the tables, that is the integral of tan x, you would have found that you would have the natural log of sec x. And you can get that from here by seeing that you've got minus 1 at the front here. If I put the minus 1 up as a power here, using the power rule for logs, that would be cos x to the minus 1, which is 1 over cos x, and 1 over cos x is sec x. So you could have written this down as the natural log of sec x. Anyway, I'm keeping it like this, so all I've got to do now is just substitute my values, my limits in. So first of all then, I have minus the natural log of the cos of pi upon 4, and the cos of pi upon 4 is 1 over root 2. So we've got that. And then minus, and I put the 0 in, the cosine of 0 is 1, and I would have minus the natural log of 1. Well, hopefully you know the natural log of 1 is 0, so this disappears completely, and so at the end of the day I have minus pi times the natural log of 1 over root 2. I could leave it like that, or I could modify this a little bit further. Okay, this is the same as minus pi multiplied by, and using the division rule for logs, I can see that this is the natural log of 1 minus the natural log of root 2. And again, if we just move that up a little bit more, natural log of 1 is 0, so that disappears, and I have minus minus, that's a plus, just simply pi natural log of root 2. Again, I could leave it like that, but some of you might want to change it to natural log of 2 to the power half. Let's just do it over here. Natural log of 2 to the power half, and this would be identical to a half natural log of 2. Putting that together with the pi, and you would get pi over 2 natural log of 2. But the volume would be equal to any one of these answers, say from here downwards, okay? So I quite like the look of this one though, because it doesn't have any fractions in it. So that's most probably where I would have stopped. Anyway, that brings us to the end of question 7.